going to start our lecture on advanced reaction engineering. So, in this lecture we will discuss about the effect of pressure drop on reactor design. That reactor is a packed bed reactor. So, we already have studied many reactors, and out of that we will discuss the packed bed reactor. So, in that packed bed reactors when heterogeneous catalytic reactions is there, let us say gas and solid phase reactions, where reactant is the gas and catalyst, that is the in the form of solid, that would be placed inside of the reactors, that packed bed reactor. That packings would be there, and once packing is there, then reactant will be charged from the bottom or top of the reactor, and then once that reactant molecules come in contact with the catalyst at if we maintain some temperature, desired temperature, pressure. So, then the reactions will take place inside of the reactor, product formation should be there. So, now if we want to design that packed bed reactor, so to design that packed bed reactors, when the reactions will take place, then we need to get the conversions, rate, concentration of the outlet of the reactor, and other things we need to know. So, let us say if the reactor is isothermal conditions, means temperatures we are maintaining constant during operations, temperature of that catalyst bed or reaction temperature is constant. So, once it is fixed, and if we conduct the reactions, then since this is the solid catalyst that would be placed inside of the reactors, there would be some pressure drop, means let us say we have reactions that we need to conduct at 10 bar pressure. So, if we use this is a packed bed reactor. So, then maybe the pressures at different location, means point to point may be different, means always when we expect or conduct any reactions, we expect that reactant molecules will contact with all the particles that is present inside of the reactors, and that all the catalyst particles take part in the reactions, active sites take part in the reactions, and then so overall rate, conversions, yields, selectivity, everything will be high. So, that is expected. So, we also expect that there is if we start the reactions with the 10 bar pressures, though throughout the reactor that should be 10 bar, but in real case that is not happen. So, point to point due to some reason. So, pressure drop is there, means either pressure increase or decrease inside of the bed of the reactor. So, therefore, that would affect the overall conversion, yield or selectivity of that particular reactions. So, today we will discuss or derive some equations for that packed bed reactors. So, that will basically study. So, here you can see, so we can study gas phase reactions, gas with solid, or means gas reactant is the gas and catalyst is the solid, that reactions we can do, or liquid phase reactions, liquid is our starting materials and catalyst is the solid. So, this way also we can, so we can conduct the reaction. So, if gas let us say liquid phase reaction, liquid and solid reactions, means liquid is the reactant and solid is the catalyst. So, in that case it is observed, or it has been also studied, that the pressure total pressure during the reaction is not affect significantly for the liquid phase reactions. So, means in case of the liquids, if we it has been observed that means the pressures does not it is not affect significantly as compared to the gas and solid reactions, means gas phase when reactant is the gas and catalyst is the solid. So, that type of reactions when we will conduct, that would affect the concentrations, conversions as well as rate of the reactions. So, if it is gas phase reactions, so the pressure changes, means pressure as a function of concentration, means if there is a changes in the pressures inside of the reactor, then that would overall affect the conversion as well as concentrations, rate of reactions, everything. So, that things we will study. So, today we will study basically gas phase reactions we will consider, and solid catalyst will placed inside of the reactor. So, how the pressures if we change the catalyst total amount of weight, so there is weight with the catalyst, how the pressures will be developed at individual points or from bed at different location of the bed. So, then with that, so how we can eliminate that pressure drop means delta P 0, that should be means there is no pressure drop, means pressure drop P 1 minus P 2 at different location, let us say point 1 is P 1, point 2 is P 2. So, that should not be there, means if we start with the 10 bar pressures in a reactor. So, then always everywhere inside of the reactor, this is the typical diagram of the packed bed reactor. So, here you can see this is a packed bed reactor. So, here bottom feed is entering and from the tops we are getting the product. So, this is the catalyst bed, so that is placed here. So, here catalyst particles is there, so you can see. So, this catalyst particles is taking part in the reactions, and here so you can see that catalyst is placed inside of the reactor. So, this is the catalyst bed, so here catalyst placed inside of the reactor. So, when reactants will pass through this, though here W is the total amount of the catalyst that is placed inside of the reactor. So, here conversions also accordingly change from the at the beginning when W equal to 0. So, to W. So, this is the total length of the reactors, if you consider this is the L or the total height, or Z also you can say Z or L, either way you can express. So, if this is the total length, so that is filled up with the catalyst. So, here if we think about this means that catalyst beds. So, here if we conduct, let us this here is the reactions right hand side we have placed A plus B going to C plus D. If we let us say conduct the reaction at 10 bar pressure. So, everywhere in locations or everywhere we are expecting that the pressure should be 10 bar, but means from point to point everywhere should be 10 bars, but due to the presence of catalyst the pressure may be different, or maybe pressure changes inside of the beds. So, that we will study. So, in packed bed reactors, this is the design equations already we have studied. The design equations we express in terms of F A naught dx by dw equals to minus R A prime. So, R A prime is the rate of the reactions for gas solid reactions. So, here catalyst is the in terms of weight, instead of other reactors we usually express in terms of volume. So, here catalyst per unit weight of the catalyst. So, we will express the rate. So, now this is the design equation, these design equations we have to use if we study this packed bed reactor. So, here we said we already have discussed for when gas phase reaction is there, whether it is we are taking in a batch systems or batch reactors or flow system. So, in batch systems volume changes would be there. So, if there is a volume changes is there, so then how volume will changes with the temperature or pressures, that we already have discussed. So, this is the volume changes for batch systems. So, here our system is not batch systems, our system is the flow system. This is a packed bed reactor and the system is the flow system. See here volumetric flow rate changes would be there with the changes of temperature and pressure. So, here small v or v naught, v is the volumetric flow rate of that at particular system. Okay. So, volumetric flow rate v, and it is a function of v naught, p naught by p, pressure is there and temperature term is there, and fractional volume change and conversion term is there. So, how volumetric flow rates each affected or changes. Initial volumetric flow rate that is entering inside of the just starting of the reactor is v naught. So, when pressure and temperature effect is there, and then volumetric flow rate will be different. So, due to the changes of temperature and pressure. So, that is written here, that already we have discussed in our previous class. So, now the concentrations we can express in terms of molar flow rate by volumetric flow rate, and molar flow rates we can express in terms of this also, that also we have discussed in our previous class. So, F A equals to F A naught plus stoichiometric coefficient for that particular species. Here's reactions is going to A plus B going to C plus D, A plus B is the reactants and C and D are the products. So, here coefficients are A, small b and small c, small d, these are the changes of moles. So, here stoichiometric coefficient for component A if we consider, so it would be minus 1. Okay. So, and for component B also minus b by A, and for other component C and D is the this. So, that already we have discussed stoichiometric coefficient. So, here volumetric flow rates, molar flow rates, and these volumetric flow rate changes, that part we will substitute here. Then concentrations we will get in terms of temperature and pressures, at the same times fractional changes of volumes and conversion, that way we can express. So, here's concentrations we can write Ca equals to Fa by V, that way. So, here we are substituting molar flow rate this, and this is the volumetric flow rate changes. So, that 2 we are substituting, and then we can write these equations this way, means here. So, already we have discussed Ca naught equals to Fa naught by V naught. Okay. So, that we are here in these equations Fa naught by V naught, that we are expressing in terms of Ca naught, and rest of the components remain the as it is. So, then finally, Ca equals to we can get this. Okay. So, we have the design equations and we have the concentrations. Now, in the design equations, let us say for a second order reactions, the rate expressions or rate law, that for a heterogeneous catalytic reactions we can write minus R A prime equals to K C A square. Okay. So, here rate constant and concentration of component E A that we have expressed, or we have put in the rate law, there it is there. So, now the concentration how they related with the temperature and pressure, that we have now derived. So, now we can replace it or we can substitute it here. So, then the equations we can rearrange and we will get in terms of this. Okay. So, this is the rate equation. So, that also we have discussed in our previous class. So, now these rate equations R A minus R A prime, that will substitute in the design equations. Okay. So, design equation for the packed bed reactors is this is the design equations for the packed bed reactor, and this is the rate equations. So, now the design equations, rate equations we are substituting in the design equations, and once we substitute these design equations, then we will get this is the equations in the differential form of equations Fa naught dx by dw equals to K Ca naught 1 minus x 1 divided by 1 plus epsilon x and multiplied with T naught by T and P by P naught square. Okay. So, then this is the equation. So, these equations we can rearrange. So, once we rearrange the equations, so in the left hand side differential form of conversions and weight of the catalyst. Since the bed of the catalyst, here catalyst bed W amount of the catalyst was taken. So, once the reactants molecules will pass through this. So, let us say A or B is reactant is passing. So, here along the length, or you can say it Z also or length. So, means from here to there. So, means from bottom to top. So, length gradually increase. So, then conversions at different locations also would be different. So, how that would affect with changing the catalyst weight, that using these equations we can find out. So, using these equations we can means will get conversions and W. So, if we change different quantity of the catalyst, the conversions will be different. So, let us say 1 gram, 2 gram, 5 gram, 10 gram, 20 gram amount of the catalyst we are using for that any reactions. So, then if we change the quantity of the catalyst inside of the beds, so accordingly the conversions also will be different. So, conversion will change. So, here's this is the final equation, differential equation that we are getting in the left hand side, dx by dw is there. So, this is if here so many parameters are there, temperature, pressure parameter is there. So, for our simplifications we can consider that the reactions we are conducting at isothermal temperature, means throughout the bed anywhere we are maintaining the temperature means outside of that reactors there is some steam jacket or temperature supply elements will be connected with here. So, here's let us say steam would be there. So, steam will be leaving. So, here. So, by that way we can maintain the isothermal temperature. So, throughout the bed. So, we are assuming that T equals to T naught, means there is no changes of temperature throughout the beds. So, one parameter we are assuming it is a constant. So, then this part we can eliminate, or for design purpose also we can if you are able to measure everywhere individual point temperature along the length of the reactor, how the temperature is changing. So, then each points you can also measure the temperatures, and that also you can put it here, but for simplifications we are assuming that there is no changes of temperature or isothermal condition in the reactors. Okay. So, now if we solve these differential equations by putting all parameters, so then we will get these are the tables we can get. So, this is required actually to means study a packed bed reactors where pressure drop is there. So, in the next we will discuss about how pressure drop with catalyst, that is coming, that part that we will discuss. So, here this is actually x a as a function of weight of the catalyst. So, catalyst weight, conversion, pressure drop, that are all are related, how they are related, that expressing in this differential equations. Okay. So, now I said this is the conversions and catalyst weight, how they are related, that we have discussed. So, now I said that if there is a means heterogeneous solid catalytic reactions is there, pressure drop would be there. Okay, delta P inside of these beds. So, there some pressure drops would be there. So, if point 1 let us say pressure is P 1 and P 2. So, that is not expected, means delta P some value would be theirs. Okay. But in real cases real case means whenever we are trying to design a reactor, so always we will expect, or ideal condition is there should not be any pressure drop inside of the reactors. If we maintain 10 bar, so 10 bar would be there, but ideally that is the ideal cases, but in real cases some pressure drop would be there. So, if we start the reactions with here 10 bar, so here would be let us say 8 bar. So, some changes are there. So, that is not expected. So, okay, so that would affect overall yield of the product. So, that may be positive or negative pressure drops. In real case industrial reactor, that pressure drop is there. So, to calculate that pressure drop inside of the reactor, so here argon equation is there. So, you can see this is the argon equation. So, we are use means we have to use argon equations. The argon equations can be used to means measures or study the pressure drop inside of a packed bed reactors. Okay. So, in the packing or catalyst materials is there. So, where this part is there. So, here P is the pressure, Z is the length. So, length means the if this is the catalyst beds, so that we can express in terms of length, that is the height of bed within that catalyst material is placed. Okay. So, dP by dz, that is the changes of the pressures along the length, we can say that. So, here G is the superficial mass velocity. So, it we can express kg of that reactant flow per unit time per unit area, cross sectional area of that reactor. So, this is the superficial velocity, means reactants we have to pass here. So, it has some superficial velocity. So, at a rate we can pass that, and Z is the length of the reactor bed. Okay. So, that bed length we consider here, the length is the bed length, and P is the pressures that we can express in terms of kilopascals, and length we can express in terms of meters. So, there are other terms also is there in that equation. The other terms the phi is the porosity of the void volume. So, volume of the void to the total bed volume, that is the porosity, and this is 1 minus phi, that is the total volume. If we subtract the porosity or pore volume, that would give the solid volumes. Okay. The solid volume volume of the solid to the total bed volumes 1 minus phi, and Gc, that is the gravity of conversions factor. So, that for SI unit we can use 1, or other units JPS units we can use some value. Okay. So, depending upon that which particular unit we are using. Here dP is the diameter of that particles of the beds, that is used, dP diameter of the particles. So, here the beds we have taken. So, here the particles we are using or placing in this bed of the reactor. So, where dP is the diameters of the catalyst particle in the form of spherical, cylindrical, any shapes we can consider, but here we are considering it is a spherical particles that the catalyst we have taken, we have charged inside of the reactor, and it has diameter. So, that is the dP diameter of the particles that is present inside of the catalyst bed, that is you need also in terms of millimeters, meters, centimeters, whatever. So, that we can write, and mu is the viscosity of the gas or that reactant that is passing through these reactors. Okay. So, mu is the viscosity of that gas that is passing through this bed, and u is the superficial velocity, the volumetric flow rates per cross sections area of the pipes. So, if we use the superficial velocity of this gas, we know, and we should know before starting the reactions, and rho is the density of the gas. So, gas viscosity, superficial velocity, density, these are the things we should know, and catalyst particle diameter and bed porosity, these are the things, viscosity, porosity. So, these are the things we should know, and pressures, G is the superficial mass velocity that already have discussed. So, these are the things if we know. So, then by means these are the parameters, means G superficial mass velocity, diameter of the particles, viscosity of that gas, and this is the void volumes or solid volumes. So, we can use this, and these are the parameters this we can put, and rho is the density of that particular gas that we are using. So, if we know these are the parameter, so that we can put in these equations, and based on that or at different locations inside of the reactors we can collect, and based on that we can use any numerical techniques or any other analytical techniques. So, by that way we can solve these equations. So, once we solve these equations, we can get pressures of the beds along the length of the bed length. So, bed length, let us say we have started with 0, 1, 2, 3, 4, 5, that is the in terms of let us say total bed height in terms of centimeter, let us say. So, then from the 0, let us say we have started with 10 bar pressures I said. So, here along the length, if it is increased, then pressure maybe slightly it will decrease. So, 10, 9, 8, 7 like that. So, that things we have to, these tables we can get by if we solve these equations, equation 1 if we solve, then we can get it. Okay. So, here two terms are there in this equation, this argon equation you can say, this term is called term 1 and this term is called term 2. So, here I have written clearly term 1 and term 2. Term 1 that is dominated that part for laminar flow, means when the gas is flowing through this bed of the reactor. So, then flow means depending upon total flow, means we know many we have studied in the fluid dynamics. So, liquid may be flow either turbulent flow or maybe a laminar flow. So, if the flow is a laminar flow, so then this part would be dominated, term 1 would be dominated, this part we can neglect, and if turbulent flow is there, so this part we should consider and this part would be dominated. So, okay. So, depending upon the nature of the flow, either it is turbulent flow or laminar flow or both the things we can keep, means when the means in general cases. So, depending upon the sizes of the particles, means the catalyst you have taken, smaller diameter, larger diameter particles you have taken inside of the bed. So, since why you am talking, so when the flow rate means laminar, turbulent, that affects with the catalyst particles. So, if we let us say this type of this is bigger size of particles, this is intermediate, this is very smaller size of the catalyst particle that will be placed inside of the reactor. So, if depending upon that, so this is the catalyst and at different sizes, its diameter smaller to larger diameter that we can consider. So, if we use smaller diameters, then the bed characteristics would be different. If we put larger catalyst size of the particles, so then the characteristics of this bed would be different. Depending upon that, the pressures of that reactor pressures, that would be also changes, that we will discuss in later in our next class. So, these are the things we should know, means argon equations we should study. So, here these equations 1 and there was another equations also, these conversions and weight. So, this equation, let us say equation A and equation once both the equations are important, so means both are differential equation dp by dz and dx by dw, means here w and length or catalyst height, bed height. So, there is some relationship. So, that also we will discuss in our next class. So, that we have to discuss, that will discuss means how catalyst means height and length or weight. I said this is the expressing z is the length and this is the weight of the catalyst. So, if z is this, catalyst would be this amount. If we further increase the amount of the catalyst, z would be little bit higher. So, like that total z's means bed height or bed length and total catalyst weight, how they are changing. So, there is any relationship or interconversion means dw and dx, how they are related. So, we can means in our next study also we will discuss means how w and function of z means catalyst weight and length, bed length, how they are related, that things we will discuss in our next class. Okay. So, then these are the two things means equations or differential equations is very important for packed bed reactor study. So, how conversions as a function of weight of the catalyst and pressure as a function of here pressure as a function of z means catalyst bed height or pressure as a function of catalyst weight also. So, these are the this equation also you can say now presently we have expressing in terms of dp by dz means pressures in the bed as a function of length. Okay. So, you consider now this. So, later we will convert it into this. So, in our next class that we will discuss more detail. So, so far thank you, today is up to this.